Hey, this is Leach with Simpson Math, and today we're talking about the normal model. We'll be looking at evaluating the 68, 95, 99.7 rule, also known as the empirical rule, and applying our knowledge from that to answer some questions dealing with the normal model. All right, so let's move on to the examples. All right, our example one is about Dr. Pepper. I'll go ahead and read it to you. It says, manufacturers of products have to make sure that they at least meet their advertised claim, including their claims of weight and volume. So suppose for a 12-ounce can of Dr. Pepper that the Temple Bottling Company has a goal of filling all cans to 12.1 ounces on average with a standard deviation of 0.05 ounces. So let's make sense of this 12 ounces. There is an implied at least sticking on that 12 ounces. You don't want to get gypped, Dr. Pepper, so they make sure that they overfill just a little bit so that way, more often than not, you have at least those 12 ounces. So let's label our normal model using the mean and the standard deviation, and also label our standard deviation. All right, so let's start with the mean in the middle, and that's 12.1. We don't have to label the units unless you want to. If you want to put the units, you can maybe stick them over here on the side that we're clearly talking about ounces. So 12.1. Well, my standard deviation, I can go ahead and label it here. It's from the mean and up 1 standard deviation, because those zeros plus 1 plus 2s, those are the z-scores. So my standard deviation is 0.05. So if I take 12.1 and I add 0.05, put those together, we should get 12.15. So if I go up 1 standard deviation, we will be at 12.15 ounces. If I add another 0.05 and I'm at 2 standard deviations above the mean, we'll be at 12.2 ounces. Add another 0.05, we'll be at 12.25 ounces, which is 3 standard deviations above the mean. All right, let's go down 0.05 each time. So if I was to subtract 0.05, we'd be at 12.05. Subtract another 0.05, we'll be at 12.0. Subtract another 0.05, and we'll be at 11.95. Just to be clear, we can say that x is being modeled by the normal model with a mean of 12.1 and a standard deviation of 0.05. So that's the shorthand for this model. All right, let's be clear what x is. So x is the volume of Dr. Pepper in a 12-ounce can. So let's write the probability statement for B. About what percent of cans are underfilled? All right, so let's be clear about what is underfilled. So if they are advertising 12 ounces, underfilled would be a time when it is less than 12 ounces. So all of these places where I'm putting a dot would be underfilled. So if it's less than 12 ounces, we're going to say it's the times when x is less than 12. So it's the probability that x is less than 12. And remember, we're not worrying about less than or equal to, because it's a continuous distribution. All right, now that we know that, let's translate this problem to a sketch of a picture. So I'm going to start by graphing my mean, which is 12.1, and a standard deviation of 0.05. And then I'm going to estimate where 12 would be. And what I'm doing is I'm going up a standard deviation, and I'm going up another one of about the same distance. So I'm eyeballing it and putting it about here and saying that that's 12. And then I'm going to shade the area less than that. So there's just a quick sketch that I am looking for this area less than 12, that's going to be my answer. Notice when you just made your sketch, you just counted down not 1, but 2 standard deviations below the mean. That tells me that 12 has a z-score of -2. I'm not requiring any z-score math on this question, but just to be clear, just to review z-scores, remember, z is x minus the mean over the standard deviation. So my x is 12, my mean is 12.1, and my standard deviation is 0.05. So this tells me that z is a -0.1 over 0.05, which simplifies to be just -2. All the questions on this assignment, on this lecture, all of these z-scores are going to be integers. That's the way that this works, right? Because look at our 68, 95, 99.7 rule. If I ask you and you get a z-score of 1.2, you don't know how to deal with that. That's what's going to be happening later. So all of our z-scores are going to be nice, pretty integers. So you don't really need the z-score math unless you want to review that. So if I have a z-score of -2, let's go back here, a z-score of -2, which is right here, and I want to find the area less than this, well, actually I already have my answer up here somewhere. The area, if I'm at -2 and I'm looking less than, it's the exact same area as if I go 2 and go greater than, which is this 2.5%. So my answer is just directly that this equals 2.5%. All right, letter C. About what percent of cans are between 12.05 ounces and 12.2 ounces? So if I'm at 12.05 ounces, notice that's a z-score of -1. If I'm at 12.2 ounces, that's a z-score of 2. So I'm looking for the area between -1 and +2, or 12.05 and 12.2. Notice we are basically converting from these values in context into z-scores. I want to draw the picture of what I just did, but just of my just the numbers I'm looking for. So again, 12.1, 0.05. This would be my 12.05, and this would be 12.2 ounces, and we're looking for the area in between. All right, let's write our probability statement. So the probability is that our x is between, so how do we write it then? It's that 12.05 is less than x, which is less than 12.2 ounces. So, few ways to do this. I'm going to come up to my completed one so I can look at the numbers. So again, I'm looking from -1 to 2. Few ways to go about this. I have my 68% here, and I could add on that orange piece. So it would be 68% plus this 13.5%, and that's one way to get our answer. So I could do 95% minus this 13.5%, and we would get our answer. Another way would be to just subtract everything that we don't want. So know that I don't want this 2.5%, and I don't want this 16%. So I'm going to do 100% minus this 2.5% and this 16%, and we'd be left with our answer. So 3 different ways. I'm going to do that last one. I'm going to take 100% and subtract 16 and subtract 2.5%. Let me explain that on this picture. I know that I don't want this 2.5% and I don't want this 16%. They're dead to me. So let me add up the areas I don't want. 16 plus 2.5 is 18.5. And then I can do 100 minus the 18.5. And we end up with, carry the 1, do all the things, and we end up with 81.5. So the probability that you just grab a random can, and it's the ounces in it is between 12.05 ounces and 12.2 ounces, is 81.5%. All right, lastly with D. The lowest 16% of cans are filled to at most what amount? Let's actually start with our picture. So we have our mean of 12.1, standard deviation of 0.05. Let me zoom in on this. And if it's the lowest 16%, I'm just going to draw a line somewhere that feels like 16%, let's say about there. And then shade the lowest 16%. So it'd be this lowest part, so the part that is the bottom 16%. And then I'm going to label this as 16%. I know that, but I do not know my 12.1. I realized on letter C, I forgot to put my question mark on that shaded region. There we go. Fix that. All right. So I don't know the x value in this case. So this is working the question backwards. So if you, so it's the probability is x is less than something. I'm just going to sort of kind of leave a blank here. I'm just going to put a light red blank right there and say that equals to my 16%. All right, so I need to figure out what z-score that is. So let me come up here to my picture. And if it's 16%, well, 16%, that's one of my numbers, but this is the upper 16%. So what I could do is flip this over symmetrically around that zero, around that mean, and I know that this is the lower 16%. So what's the z-score attached with that lower 16%? Well, that's that z-score of -1. And I already figured out earlier that if I have a z-score of -1, then I'm at 12.05 ounces. So my blank is actually 12.05 ounces. So the probability that I grab a random can and it's less than 12.05 ounces is 16%. All right. This particular one, I encourage you to, after I read a question, to pause the video, try it on your own, and then answer the question, and then see me answer the question, and hopefully you got it right. All right, example 2, rivets. A company that manufactures rivets believes that the shear strength in pounds is modeled by this normal model, 800, 50. So this means what? What's the mean? What's the standard deviation? So the mean is 800, and our standard deviation is 50, just to be clear. They didn't define an x for us, so let's define an x for them, that x is the shear strength of a rivet. I have a little picture down here just to explain what a rivet is and shear strength, what the shear strength is. So this is a rivet. It kind of looks like a screw, but without the screw part on it. It's just this bolt, basically. We use it, it gets stuck between two sheets of metal, and then mechanical press will pound out this end to flatten that, which will then basically stick these two pieces of metal together. But at some point, if there's enough force pulling on in opposite directions on this rivet, it's possible that this rivet could just break. It could just shear apart. Okay, that's not good. These rivets hold together like wings on a plane, bridges, like pieces of metal that hold a bridge up. You don't want these things to break. If these things break, bad things happen. So when the rivets break, they call it shear. So that's what it is. That's what you're finding. All right, so let's go ahead and actually do letter A. So we're going to label the horizontal axis with these 7 numbers, and don't forget about S. So pause the video, try that on your own. All right, welcome back. So we've filled in our numbers, and so what this does for us is this shows us the relationship between our numbers in pounds and then also then what these z-scores are. All right, let's take a look at letter B. Would it be safe to use these rivets in a situation requiring a shear strength of 750 pounds? Well, let me give you a little bit of a hint on this. Find this. Find the probability that X is less than 750 pounds. This would mean that the probability that you pick up a certain rivet, just a random rivet out of the box or that was made by this manufacturer, and its shear strength was less than 750 pounds. So what is that probability? All right, and then if you want to then answer that question, it's would it be safe to use a rivet that would require 750 pounds? Pause the video and try that on your own. All right, welcome back. So I started with just my picture. So here's my mean, my standard deviation, estimated where 750 would be by dropping down 50, which means I have a z-score of -1. Or I could have just looked at my picture drew early and saw that my z of -1 is tied with the 750 pounds. And then I go to my graph I made earlier, that if I'm at -1 and I'm looking for the area less than that, That's the same thing as being at positive 1 and finding the area greater than that, which is 16%. So imagine that if 16% of the bolts on the wing of the plane that you most recently flew on had a pretty good likelihood of just breaking and falling apart, would you want to fly on that plane? No, right? So these particular rivets should not be used in a situation requiring that strong. Maybe only 650, but probably actually less. All right, these last two are much more straightforward. C, about what percent of these rivets would you expect to fall below 900 pounds? Go ahead and pause the video and try this one on your own. Alrighty, welcome back. So first, I drew my picture. So I knew that I had a mean of 800 and a standard deviation of 50. To find the 900, I had to go up 2 standard deviations, up a 50 and up another 50. So that gives me my z-score of 2. I can go up to my picture, my 68, 95, 99.7 rule. And if I'm at a z-score of 2, I'm looking for the area less than. I'm looking for all of this. Well, I can also just find the area above 2, which is 2.5, and subtract it from 100. So that's what I did. So everything adds up to 100, and I subtracted 2.5 away from it, and we end up with 97.5. Now you could have figured out that the middle 95% is, well, 95%, and then this last little bit is 2.5%, and added those up, and then you would still end up with 97.5%. All right, our last question for this lecture. D, the top 2.5% of rivets would have a shear strength of at least how many pounds? So this is one where I give you a percent, and you have to turn it around. Go ahead and pause the video and try this one on your own. All right, so welcome back. So again, I start with my picture. It's the top 2.5%. So I know I just estimated where 2.5% was. Said, well, it's probably about right here. But I know that 2.5% is one of my special numbers. That's when my z-score is 2. So then when my z-score is 2, actually from our last problem, we know that that's tied with 900 pounds. So that means that the top 2.5% of rivets would have a shear strength of 900 pounds. So I just put it together with that probability statement, or to answer the question, it's just 900 pounds. All right. So I hope this helped you understand the empirical rule with the normal model a little bit better. The next step, the next lecture, is going to be covering what happens when I don't give you a nice little integer. What if you end up with a z-score of 1.57? How to deal with that. But in the meantime, we need to make sure that we understand this normal model. The best way to do this is to get our hands dirty and to use it using the 68, 95, 99.7 rule. I hope this helped, and I'll see you next time.